Okay, so in the first video of the chain rule, I went through not only I'm going to discuss the formula, but went through some examples really slowly, trying to anticipate a lot of your questions in terms of being introduced or reintroduced to the chain rule after only receiving it when you were burned out last April. But the chain rule, like I've said in the previous video, is simply the derivative of composite functions. And as long as you remember that, and you remember that composite functions are layered functions, you should be just fine. So we're going to go ahead and do some examples, probably a little bit quicker in this particular video, and we'll pick up the pace even more in successive videos. Not quite sure exactly how many of these we're going to have in the end. But I'll do them until I think that we've had a pretty good sampling of all the different variety of chain rule problems you're likely to see. And of course I want to hit, power rule. I want to hit some radical functions, which are of course a species of power functions. I want to hit some trig. I want to hit some exponential. And so I also want to maybe do one or two equation of a tangent line sort of folded in here to keep those skills a little bit sharp. So let's go ahead and jump right in. If we're given y is equal to secant of 4x to the fifth, the question then becomes, what is the outsidemost function? Okay, the outside layer, and of course it's probably easier if we put parentheses right here. The outside layer is the secant. So this is secant stuff. Okay, this is secant of something. You don't really care about the something at the very, very beginning of taking the derivative, because really what you're worried about is secant tangent, right? You know that that the derivative of secant stuff is secant stuff, tangent stuff. Okay, so we just need to go ahead and replicate the stuff down in here, and then of course the very next thing that we need to do is go ahead and show the derivative of that stuff. Okay, now remember the chain rule tells me that when I differentiate f of g of x, I'm going to get f prime of g of x times g prime of x, and that is exactly what I have right here. This right here, and it's a little bit difficult because secant becomes a product of two functions, right? But you can't just go secant tangent and not give an angle measurement expression to secant. It has to be secant of that angle expression and tangent of that angle expression. This right here is your f prime of g of x. This right here is your g prime of x. And of course this right here is sort of the analytic form of that differentiation rule. Okay? Now, let's go ahead and let's do something that's related to that. Let's say y is equal to secant to the fifth of 4x. Now that's different, right? Because here, part of the angle expression is being raised to the fifth power. Here, the entire function is being raised to the fifth power. So this is really equal to secant 4x to the fifth, whereas this is not, right? And so the most outside thing happening here is to the fifth. So whereas the outsidemost here was secant, and this was secant stuff, this is stuff to the fifth. And so when we take the derivative, we have 5 stuff to the fourth. Now I need to take the derivative of that stuff. Well, even that winds up being a composite function, right? And so what I have here is I have secant 4x tangent 4x times 4. And so really what we have here is a composite function, not f of g of x, but f of g of h of x. So remember when I said that composite functions were layered functions? Well, they're not always 2 layers. This one was indeed 3 layers. And if we actually want to go ahead and identify them, we can identify the f as x to the fifth. We can identify the g, meaning the middle layer, as secant x. And we can identify h of x as the 4x, okay? And if I actually want to bring all these together, okay, let me sort of try and move this. Only so much room on my desk. F of g of h of x winds up being secant of 4x to the 5th, which is of course what I have up there. So instead of the chain rule giving us f prime of g of x times g prime of x, it's going to be f prime of g of h of x, peel a layer off, g prime of h of x, peel another layer off, h prime of x, okay? So basically what you need to do is you need to be able to look at a function and identify the layers of that function based upon understanding how a composite function is structured. And you basically just need to keep taking the derivative of the outside and then just peeling off a layer, taking the derivative of that next layer and then peeling that layer off as well until there's nothing left, okay? Obviously this has 3 stages because this original function has 3 layers, okay? But notice the similarity between these. This function and that function had a lot of things in common, but they had different things, they had those things going on in different orders, and therefore I had to structure it just a little bit different in order to get that derivative, okay? Now, let's go ahead and do another one. This one is f of x is equal to 1 plus cosine squared 7x cubed. Okay? Now, we need to ask ourselves, what is the outermost thing that's going on? The outermost thing going on is the cubing. Okay? Is the cubing. But in order to actually get at this a little bit better and actually see the layering, we need to take the trig function out of lazy man's notation, right? Remember that square right there says the whole function is squared. But the reason why they put the squared there instead of writing it like this is because mathematicians are lazy, okay? And, you know, in a good way, right? Because you want to be efficient as you can in terms of notation. But sometimes that efficiency comes at a cost. The efficiency coming at the cost here is that this doesn't communicate the layers of this composite function as well as this does. This communicates it a little bit better. So what's happening, what's the most inside thing? If I were to actually plug something in for x, I would multiply it by 7, then I would cosine it, then I would square it, then I would add it to 1, and then I would cube it. Well, of course, the layer, that's going from the inside out, okay? The layers of the composite function are from the outside in. So if I were to go ahead and take the derivative of this, I need to deal with the outermost layer first. Okay? That was stuff cubed. Well, stuff cubed becomes 3 stuff squared, okay? Now I need to deal with this next layer in here, right? This squaring right here. So that becomes 2 times cosine of 7x. That's another layer done. Now I'm going to get negative sine of 7x as I take the derivative of the cosine. And now I need to take the derivative of that angle measurement. And now I've taken the derivative of the cubing, stripped that layer off, taken the derivative of the squaring, stripped it off, taken the derivative of the cosine, stripped it off, and then taken the derivative of the 7x, the linear right here, that's the angle measurement expression, okay? And that actually was a 4-layer one. And your teacher will probably want you to combine the numerical factors, right? The 7 and the -1 and the 2 and the 3. So let's go ahead and perhaps we can sort of put some of that together. We get negative 42 sine 7x cosine 7x and then 1 plus cosine squared 7x squared or something like that. And that would be just about as simple as you can get it. Now obviously, you know, you can go a little bit further because that right there can be forced to act as a double angle identity, if you remember that from trig. but let's not burden ourselves with that when we're actually really should be looking at chain rule examples and concentrating on the calculus and not the trig. But the trig being very important, let's not forget it. And if you're not looking over those identities in an ongoing way, just because I'm not giving you cumulative quiz, because I'm not there anymore, the cumulative quizzes, every single one of my kids who I've actually asked came back and said that as much as the cumulative quizzes were a burden while they were taking them, they helped out enormously on the AP exam. And while I'm not there and able to give you cumulative quizzes every Friday now, you really do need to be keeping up with a couple of things. Those couple of things being unit circle values. You need to be keeping up with trig IDs, the fundamentals, and then the sum and difference and double angle identities. You need to try and go ahead and look back at some of the geometric formulas because you're going to be needing those before long. Just logarithmic and exponential rules and stuff like that. So be on the lookout for that. Now let's say that I'm actually given sine of x squared. Okay, that is a composite function. The outside layer, of course, is sine, right? It's sine stuff, but the stuff happens to be x squared. But let's say that I'm actually asked, not for the first derivative, but let's say I'm asked for the second derivative. Okay, well let's go ahead and find the first derivative first, okay? Now I know that this is going to be sine of stuff, and putting parentheses right there communicates the layering a little bit better. So it's sort of like a visual cue for us, so don't be afraid to actually go ahead and change the notation, as long as you do so legally, to communicate the composition a little bit better to you. So I know that it's going to be cosine of stuff times the derivative of stuff, okay? And of course, if that's going to be 2x cosine of x squared. Now, when I take the second derivative, I have to notice that whereas I did not have a product in the original, I now have a product function. But is the product on the outside, or is the composition on the outside? Meaning, is this going to be product rule inside of the chain rule, or is this going to be chain rule inside of the product rule? And again, we run back to order of operations and ask ourselves, if we were to plug in a value for x, what would be the last thing that would be done? And the last thing to be done would be the product. So the product is the outermost thing going on here in this particular function right here. And therefore the product rule is going to be the biggest thing that's going on in the derivative. So the chain rule is actually going to wind up going on inside of that, right? And let's go ahead and designate our u and our v for our product rule. Now you can include the 2 in u, or you can pull the 2 out in front and treat it as a coefficient that comes along for the ride. I don't really care. I'm just going to go ahead and include it with u so I don't forget it along the way. Now, I know that I need u. Now let's take the derivative of v. Now what's the derivative of cosine of stuff? Well, the derivative of cosine of stuff is negative sine of stuff times the derivative of stuff, right? Well, then I also need to take u prime over here in this other term and then have cosine of x squared. And of course, we'll go ahead and put the parentheses around the x squared. This winds up being 4x, or negative 4x squared sine x squared plus 2 cosine of x squared. And, unless you want to reverse the order of those terms, so you have the positive term first, which, is more of an aesthetic thing than really hardcore simplification, that's pretty much the second derivative right there. Okay, and of course you haven't gotten to the point where you've probably discussed in your class what the significance of that second derivative is, but you need to be well versed in actually finding that second derivative when you're actually asked for it, because that actually does have import. Okay, and those of you who are in physics probably already know what the second derivative refers to. If the original function is position and a derivative is a rate of change, the first derivative is a rate of change of position with respect to time. Velocity. What is the change of velocity with respect to time? It's acceleration, okay? So it's a rate of change of a rate of change. So the second derivative, if you want to put it in terms of like particle motion or some sort of physics scenario, second derivative is acceleration, whereas the first derivative is velocity. So very, very important. Third derivative usually doesn't get used. Third derivative is a change in acceleration. In physics, I think that's called a jerk, which I just think is kind of funny. Makes me hungry for Cajun food. That's pretty much it for this video. Let's go ahead and call it quits on this one. I'll pick up in part 3 of the chain rule videos with a few more examples, perhaps get a tangent line question in or two, and then we'll move on from there.